Welcome back, OChem 1. I am so excited. Let's take what we just learned in the last video about aromaticity and let's put it into reactions. How fun. This is one of my favorite sections because we get to take a little bit of what we've learned all semester, but now apply it to something that's been around for a couple hundred years and is a huge, some of these reactions are huge industrial processes. So it's still really relevant chemistry. In fact, one of the processes I'm going to show you a little bit later in this video makes tons, I mean literal tons, like I'm not just exaggerating, actual tons of starting materials that are used in this country every year. So it's pretty cool because it's directly relevant. It's huge industries in chemistry, and it's also chemistry that just works. It's been around for a couple hundred years, so it's pretty cool. Just like my other videos, I've got a million web links in here for you to take a look at. What we're doing is called electrophilic aromatic substitution. So fun. So I want to start with a really oldie but a goodie. We're going to start with benzene, and we're going to do something called a nitration. So we're going old school, and we are going to mix sulfuric acid, nitric acid, and we are going to add a nitro group to our benzene. And then when we turn around and do some synthesis, we're going to use this and make some TNT. Isn't that going to be fun? Awesome. All right, so, I mean, not for real, on paper. Well, on an iPad. So let's take this and let's draw the mechanism. Our benzenes, if we put a ranking out there of our nucleophiles, let's go all the way back and let's look at the nucleophiles we have seen this semester. We've got things like our cyanide, our N3, our azids. We've got some really good nucleophiles. And then we've got, oh my goodness, I guess I'm a little tired. We've got things like ammonia, which are super good. And then we worked our way into our things like booze, water. We saw those could be nucleophiles. And then we worked our way into alkenes. Okay, so now, and then one of the things we haven't talked about yet is alkynes. They can be all kinds of fun. I'm sorry, I couldn't resist. We've got alkynes. They can be nucleophiles. And then way down here in our reactivity, the bottom of the barrel, but still a nucleophile, is our benzenes. Okay, so we're going to increase our reactivity this way. So they still work, but we're going to draw a huge colored line here because these are going to be really pretty special, and we are going to use completely different reagents here. So that means on your synthesis, you don't really want to mix and match. So I'm going to teach you how to do a nitration here. You don't want to turn around and try to do that with booze or with an alkene. You're not going to get the same chemistry. You're going to make road tar. So we're going to keep these separate. That's why they're at the end of the semester. We're going to keep these separate and very specific. We need something very reactive with our benzenes. And I'll show you what I mean. Let's draw our mechanism. All right, here's what's fun about electrophilic aromatic substitution. All of our mechanisms are going to follow the same type of pattern because benzene is so unreactive as a nucleophile. Our electrophiles got to be a huge kick in the pants. So I'm not even going to draw benzene first in my mechanism. I am going to draw nitric acid. I know, right? You didn't see that one coming. Okay, let's go back to a definition that I gave us way back in the beginning in our acid-base section. What makes something an acid and what makes something a base? We had three different definitions, and then we got to definition number 4. It depends what it's mixed with. This is one of those cases. If I mix sulfuric acid and nitric acid, which one is stronger? Our nitric acid wins. This, believe it or not, is going to have the lower pKa. So if I mix nitric acid and sulfuric acid, guess what? Nitric acid is a base. That sulfuric acid is the stronger acid. It is strong enough to literally protonate nitric acid. Okay, now wait for it. Let's protonate that. And what are we making? We're making over on this side of our nitric acid, we just really made water. So if you start over here, you can literally dehydrate nitric acid and lose water in this mixture. Okay, this is ridiculous, but this is how that works. And what we just made in this process, oh, I'm going to need another page, aren't I? In this process, I just made, okay, now watch this. Okay, this part stays the same, but now look what you just did to your nitrogen. Okay, this is legitimately a positive. This is an actual nitrogen cation. That is not a formal charge. Okay, up here you've got a positive and negative balancing each other in that structure. That's a formal charge. This is an actual charge on nitrogen. What we just made is a super electrophile. Oh, I'm running out of space there. Sorry. Now we're ready for benzene. Okay, let's take our benzene. And now we can take a wimpy nucleophile because we just made a super electrophile. So now we can swing out, put those electrons back on oxygen. And now what did we just do to our benzene? Okay, hang on. So now we just swung out. I'm going to go up here and give myself some more space. We left a carbocation. We have, and then we left. Now we're back to a formal charge on our nitrogen. Okay, now hang on a second. Let's go back to the video we just watched. This is aromatic. Is this aromatic? No. This is why benzene is so unreactive compared to some of our other nucleophiles, because you disrupt being aromatic. So, but that's good news also, because the next step, okay, there was a hydrogen here. Let's put that hydrogen back in. The next step, you can't stop. This step is your slow step. This would be your rate determining step. As soon as you make that carbocation, that is phenomenally fast, because if you can eliminate, let's do an elimination here. We've got the conjugate to sulfuric acid, or we've got surely something floating around in here that can take that hydrogen. Now watch these electrons. They're going back to fill in. That's just like an elimination reaction, only it's very specific, because what did we just do to our benzene ring? We just restored that aromatic ring, and we substituted that NO2 group. Okay, so all electrophilic aromatic substitutions are going to follow this exact same pattern. Okay, number one, you make a kick in the pants electrophile. Okay. Then step number two, you use your benzene as your nucleophile, but that's definitely your slow step. And then step number three, you eliminate. And you're always going to eliminate that same hydrogen, because you have to restore being aromatic. And that hydrogen is your ipso hydrogen. Isn't that just fun to say? It is ipso because it's on the same carbon that you're substituting. Okay, so they're all going to follow this process. This is just our first and one of our oldest reactions, and this is our nitration. Isn't that fun? All right, so let's do another one. Okay, our nitration's been around for at least 150 years. Friedel-Crafts has been around for probably close to 100 years. I'm embarrassed to say I didn't write out the year on this one, but it's been around for quite a while. Our Friedel-Crafts, we have 3 different versions of the Friedel-Crafts. Let me give you a little list, and we will draw the mechanisms for probably at least 2 of them. They're all the same. We're going to follow the exact same process. Okay, we can add a halogen, and that could be chlorine or bromine. Notice we didn't use chlorine and light. Okay, that wouldn't work. We have totally different reagents for our benzenes. Okay, we can add a carbon. That is called a Friedel-Crafts alkylation. And then finally, we can add a ketone. And we are going to do something called a Friedel-Crafts acylation. Okay, all 3 are going to follow the exact same process. All 3 put a nice functional group right on your benzene, and they all follow the same mechanism. Let's start with this middle one. Let's start with that Friedel-Crafts alkylation. Let's take our benzene, and do we start there? Heck no, I just tricked you. All right, what do we do in our mechanism? We have to make a super electrophile. So let's take any kind of alkyl halide. Why don't I draw the bromine since I put the chlorine over there? And we're going to mix it with a really good Lewis acid. Okay, what makes aluminum a good Lewis acid? Remember, it has space right here. We can bond with another lone pair. I mean, aluminum has only got 6 electrons around it right now, and it really can take 8. In order to make the octet rule, it's got space for 8. It's just only sharing 6. So it's got this big empty space. That's what makes it a really powerful Lewis acid. Out of this whole substrate here, where do you actually have lone pair? On your bromine. So your bromine are going to fill in that space. Now what that does, I'm going to use my 1980s air quotes, because what that does is it literally forces your alkyl halide to leave. So you can have an intermediate where you're showing the complex of all of this. I'm going to go straight to that bromine has just left the building. And why did I draw electrons there? And bromine, of course, being more electronegative, has just left, and we have made this. Okay, and then this doesn't last. Okay, this by the time you work that up, you're going to end up making all kinds of aluminum hydroxide salts and all kinds of bromide salts and just a whole crazy mess. But in the middle of all of this, what you just made was a carbocation, and you just forced that to happen. Your aluminum bromide just helped you make a carbocation. And son of a motherless goat, do you think these can rearrange? Oh, yes. Just like Unit 3 and Unit 4, your carbocations can rearrange. In this case, there's nothing to rearrange. They're both the same. So then let's continue our mechanism. If we have a carbocation, we know that that's a phenomenal electrophile, right? You've got this big black hole missing electrons. So let's take our benzene and let's take our newly formed carbocation. I'm just going to draw it to the other side. And now we can follow our same process. Now our nucleophile is strong enough to react with that super electrophile. That's our super electrophile. And then what happens to our benzene? Well, we just formed a bond to that ethyl. And what did we leave behind? A carbocation. But is this going to last? Remember, this is aromatic, This is not. So this next step is going to be so fast. That is that elimination ipso. Okay, we'll have probably one of our Br minus there. It's going to take that and reform your benzene every single time. So now what we just did was substituted our benzene and reformed that aromatic ring. So what you just did was literally substitute whatever was on your alkyl halide onto your benzene. And that's really powerful. You can add all kinds of stuff using the Friedel-Crafts reaction. Now what you do have to be careful of is a carbocation rearrangement. So let's say I take something like, let's take something like this. Okay, what carbocation are we about to make? All right, there you go. Is that going to stay? No. You are going to rearrange that faster than you're going to react. So how are we going to rearrange that? Well, that's a primary carbocation. That is going to rearrange to something better very quickly. And now your benzene is going to react. So now your benzene is going to add right into that carbocation. And then again, now you've just substituted. Only this time you made an isopropyl because you did a carbocation rearrangement in there. Oops, I don't want this bond there yet. Hang on. And then we have to do that elimination, that ipso elimination. So we'll have something in here. And then now we just substituted onto our benzene. And at the end of that process, we just put an isopropyl on our benzene. And we just make cumene. We're going to see that in a little bit. All right, so what about the other iterations? They follow the exact same process. So let me just show you the other two. Okay, you can add a halogen. You can add chlorine or bromine. Again, notice I did not use light. Oops, Br3. And now what you're doing is literally making a positive chlorine or a positive bromine first. So you can do the math on that. We've never seen anything like that. That's going to be crazy reactive. So your benzene will then add into that positive, and you will end up with a nice intermediate of either chlorine or bromine that looks like that. And then we eliminate. And then you end up substituting and having your halogen on your benzene ring. So again, don't goof up and use chlorine or bromine and light. Not going to go there. If you want to put a halogen on your benzene, you have to use Friedel-Crafts. And then that last one, this one was super fun. The acylation blocks the carbocation rearrangement. Okay, I got to say that again. So let's say on this one, you did this reaction, and what you really wanted still was to add that propyl group, but instead you got isopropyl, and you were just annoyed because that's not at all the compound that you wanted. You wanted your carbons in a straight chain. So the way around it, it is a two-step process, but you can do the acylation with an acid chloride. And what happens is that your lone pair on your leaving group, and let's go ahead and write this one out, your lone pair on that oxygen, okay, watch this. Now let's imagine I've got my aluminum in here and we're filling in that space. Well, it doesn't have to just be right here. This lone pair on oxygen are going to help that process. So your actual intermediate is so funky, but it's real. It is called an oxonium ion, and it is like that. So then where does your benzene react now? Again, we're going to react the same way, only how do you give lone pair back to oxygen? You react right here. Okay, so then what does our benzene end up looking like? It looks like this. And we just made, this is super fun, a ketone. So then do we do that same ipso elimination? Absolutely. Something in here is going to take that. There you go. And so at the end of this process, I gotta draw up here. I'm gonna run out of space. At the end of this process, we just made a ketone. And we reformed right here. And we formed that bond. Okay, let me put brackets around that because that got a little bit messy. So remember, for these electrophilic aromatic substitutions, we literally follow that same process for our nitration and our Friedel-Crafts. Number one, we make that super electrophile each time. And then number two, you use your benzene to make your super electrophile. Then your benzene can swing out and react with whichever. And then you will always, always eliminate that ipso hydrogen because you have to form the aromatic ring again. And it has to be that ipso hydrogen or you're not in conjugation in your ring and it's not going to happen. So each one of these, between the nitration and the Friedel-Crafts, they all follow that same process. Each one of the mechanisms, the only difference might be your super electrophile. It might be something different. All right, then we've got some other old school processes with our benzenes that we're not going to draw the mechanism for. I want to show you two radical oxidations. The first one is an industrial process, and it's how we make phenol. And phenol is incredibly old and useful. I included a nice Wikipedia link here to this industrial process. If you're curious, as soon as you see the mechanism, you'll realize why we didn't draw it. It is radical, so we're not going to draw the process, but how they make phenol in literally ton amounts in this country, because it's such a powerful starting material in all kinds of things, is they use a radical initiated process under oxygen atmosphere. They're doing an oxidation. So let's call this a radical initiated oxidation. And what's super awesome about this process is it's 2 for the price of 1. What they make is phenol, which is a huge, huge chemical industry. And the byproduct is an even bigger industry, and that is acetone. So literally it's 2 for the price of 1. You take your benzene, which we can get from the petroleum industry and crude oil products. We can take propylene, and wow, those two are coming from the petroleum industry, huge feedstock, a little bit of oxygen and a radical process, and you just made 2 huge industrial compounds in industry. So that's pretty cool. So we'll use some phenol in our synthesis, and of course we use acetone quite often if we were in the lab. And then the second one you've seen, and that is KMNO4. Okay, just KMNO4 on a benzene ring. No reaction, nada, nothing's going to happen. It's radical. Okay, it's radical. Like this cumene process, okay, it doesn't start on benzene. It starts here. So KMNO4 does nothing to benzene. But watch this. If we have some kind of alkyl group and we add KMNO4, now we're about to make another huge feedstock chemical, and that is benzoic acid. Okay, now why? All right, hold the phone. I'm feeling a moment here. Let's look at our list of radicals and carbocations. When we ended class before spring break, we got to the place where we drew out this one. And we said, wow, this radical was actually pretty awesome. Or carbocation. And then we went from there and we saw tertiary was pretty good. And then we went even farther and said, secondary is decent. Okay, but then primary, boy, that just super sucks. And so on. Okay, and then finally, boy, if you just have methyl, yeah, you're out of luck on that one. But I'm going to add to this list that next to a benzene is our best possible. Look at that. So next to a benzene is called benzylic. And that benzylic radical or carbocation, above all else, is the most stabilized. And then allylic is second to that. So for KMNO4, an actual radical on benzene, not going to happen. Aha, but a radical right here next to benzene, totally going to happen. So whatever is attached here, you just break those bonds and lose it. So whether you have a methyl group, an ethyl group, anything over here with KMNO4, you are going to make the exact same thing, and that is benzoic acid. Okay? Awesome. All right, so now let's do a reduction. We just did 2 oxidations. Let's do a reduction. Okay, this is what kicked off a whole lot of our benzene discovery 200 years ago, was the fact that they don't do regular reactions. So one of them is a hydrogenation. This doesn't work. The other one was bromine. Bromine and light just doesn't work. And bromine and DCM doesn't work on benzene. Both of those reactions are going to work on alkanes and alkenes, and they just don't work on benzene. It's crazy. So does that mean you're out of the water? No, modern day metals, we have lots of options. So you can get this to work. You have to change your metal. Platinum is pretty popular. We can use platinum for that. Nickel is another one. There are a couple metals that will do that reduction, and you will go all the way. And you will still have cis. So let's say you have 2 methyl groups on here. If you do that reaction, you will end up with cis. Not trans. It's still like our hydrogenation from our last unit. You're going to be on the surface of a metal, so they're going to happen on the same surface. Okay, so you can reduce a benzene. You just need a little bit more of a kick in the pants in order to do it. Oh, and then I do want to show one more catalytic reduction. So something that our hydrogen and palladium does work on, or an old school was tin or iron, but I'm just going to go ahead and show you the hydrogen is our NO2 group. So this can work with other metals as well. You can use a metal catalyst. And now we made another huge industry in that country, and this is aniline. So you just went from your NO2 group to an NH2 group, and we're going to see in the next video that these two are quite important and they have complete opposite reactivity. So this is how they make aniline. You take and you nitrate your benzene first, and then you reduce that NO2 group for an NH2 group. So you can use various metals in there. If you want to tell me, palladium, that would be okay, but I'm not sure if that's the standard, is palladium for that. Okay, I love it. And then we can't go too crazy until we actually talk about some organometallics. So let's get a little bit more modern. Our benzenes, like I said, this chemistry, some of this chemistry has been around for between 150, 170, 180 years. Let's get a little bit more modern. We saw our Gelman and we saw our Grubbs. Now those are in the 2000s. The Heck coupling started a little bit before then, but has certainly become more mainstream in the 2000s for this coupling. And what's awesome is you can take an either chloride or bromide on your benzene, so bromobenzene or chlorobenzene, each one, or as long as you've got a halogen there. So I'm going to say, or you can do either one. Okay, and then you treat that with a palladium catalyst, and you can add an alkene. So if you were to mix this one plus this one with a palladium catalyst, you can do a coupling reaction. Okay, remember our coupling reactions are organometallic. We don't draw that mechanism, but you're literally sticking two carbons together, just like our Gelman, which is on the test you guys were just taking. And we've also seen that with our Grubbs. So what do you get at the end of this process? Now you can really start to substitute and get some conjugation in those aromatic rings. Now you can put a double bond there. Okay, now let's just make a comment. You have to have aromatic chemistry here. So we have to have only our benzene reactions that I'm showing you here. But now if you've got a regular old alkene there, well, now that's fair game. You can use your unit 4 reactions there. So let me give an example. Would ozone work here on benzene? No. Would ozone work here? Yes, because it's not on your benzene ring. You can still do those other, reactions there next to your benzene. Just not going to disrupt the actual benzene ring. So I know that this was a lot of information very fast in one video. So I made this little chart that I thought that we could just do a quick fill in, but then you can of course take this and fill it in with a little bit more detail, because we're going to take this little flow chart and do synthesis on our next video. And then our entire Unit 5 test will be just these benzenes and just doing some synthesis. So let's do a little fill-in at what our benzene can do and the things that we just learned how to make. All right, so let's start with this one. We just did this one. This was our hydrogen and platinum. You could do that. All right, these are our Friedel-Crafts. So if we wanted to make that, we would need some kind of chloride and that aluminum chloride. Oh, and we just did this one. This is KMNO4. This is our Friedel-Crafts. Ooh, let's just not call it Edelcrafts. That's a Friedel-Crafts. So this is our Friedel-Crafts, and this would be that acid chloride. Okay, awesome. Oh, we did the nitration. That would be our nitric acid. And then we can reduce that nitro group to the aniline. And then this was our cumene process. And then finally, how did we add chlorine? That is also our Friedel-Crafts. And that is like this. Okay, that's our little aromatic flow chart. All I'm going to do on our next video and on your test is mix and match these reactions. Everything we want to make is going to be right from here. So you may want to download this one and add your own detail to it, and it'll be your cheat sheet for this next test. All right, so our next video, I'm going to stop this one so it's not too long. And then our next video, we're going to take these benzenes and we're going to put them into synthesis. So let's mix and match some of these steps.